So on page 7, how far did we get? Did we get through the full first page? We finished. Okay, we did 1 through 3, right? Or we didn't do number 4. All right, so let's try number 4. This is table of values. Okay. Part A, use 3 left-handed rectangles with intervals indicated by the table to estimate the area between the curve and the x-axis. Okay, so make sure we pay attention to our endpoints here. We're starting at 0, ending at 7. We want to split them up into 3 subintervals that all span across the same number of order pairs. So we can do 0 to 4, 4 to 6, 6 to 7. First subinterval has a width of 4, right? 0 to 4 is 4, 4 to 6 is a width of 2, 6 to 7 is a width of 1. And then within each subinterval, we pick the appropriate height that represents the height of that particular rectangle. Okay, so this left-handed rectangle. So first subinterval, we want to choose the height coming from the second row. So remember, first row is going to give you width information. Second row is going to give you height information. So first rectangle has a height of 5, so 4 times 5, because 5 is the left side of your subinterval. Second subinterval has a width of 2, a height of 3, so 2 times 3. Third subinterval, width of 1, height of 2. Okay, so go ahead and try B through D. I want us to walk around and make sure that you guys are comfortable with pulling this information. I think this is easy, but also understand, it's easy to misinterpret information. I see students picking off the height from the top row, or they are adding instead of subtracting to get the width. So, but once you know how to get information, then it's not hard, but it does sometimes take some time to get used to it. So the key is attached, but I want to see how you guys do with this. Good, got it. Guys, the middle rectangles, you're only picking off whatever the middle height value is. You're not going to do anything with average. Okay, you're not going to do anything with B minus A over N. And also middle is kind of like in quotes. Okay, it's not directly the midpoint. It's just going to be whatever is between your two endpoints. Okay, are you okay? A through C. On the quiz tomorrow, expect you guys to memorize the formula for trapezoid. And 1/2 width, height 1 plus height 2. Make sure that you don't try to do any of the trapezoid rule with doubling all the middle heights. We don't want to do that. All the heights are different here, so we're going to have to just do, in this case, 3 separate trapezoid areas and add them together. Another common issue that I see with trapezoids is, especially if your intervals spans across multiple order pairs, every trapezoid is only going to pick up 2 heights. Okay? Even if you see a bunch of heights in between, you're only going to use the ones at the ends. Right? So I see some students add all the heights that they see in front of them because they feel like they have to involve those order pairs that got skipped over. So in this case, we don't really see that because there's only 2 heights to choose from. But if my interval is spanning across 4 order pairs, I'm only using the heights at the end. Never going to have more than 2 heights associated with each trapezoid area. Okay. Okay, questions here? Okay. All right, let's go to page 8. Let's do a limit definition. So number 5. Okay, I will give you the limit definition area. So this is what I will give you on the quiz. So the width is d minus a over n. Your left endpoint is your a, and your right, and then your width is again d minus a over n times I. Okay, so go ahead and set up. Number 5 and go through your steps. Page 8. Let's see. Okay, so first find our width, 2 minus -1 over n. We hold on to that n variable. Eventually that will get pushed out to infinity. Start putting into our formula. Width is 3 over n. A is -1 plus 3 over n times I. Get this out of function notation. So 6 minus parentheses squared. Okay. Or g of x, rewrite your function with a space reserved for your arguments. So then your -1 plus 3 over ni will get inserted into the space there. So 6 minus -1 plus 3 over ni squared. You're going to FOIL out your parentheses, distribute the negative through. Then work in the 6 and 1 can combine, and then finally the width component will start distributing through. Separate each of the coefficients away from the summation rules that you're going to apply. Summation 1 is n, summation I is n times n plus 1 over 2. Summation I squared is n times n plus 1 times 2n plus 1. And all the degrees within each fraction should match. Degree 1, degree 1, degree 2, degree 2, degree 3, degree 3. Pull out all the coefficients that you need to match up. So 15 over 1, 18 over 2, minus 54 over 6, combines to be 15. Okay, number 6. Find the most general antiderivative. So this just means take the antiderivative of this expression, but we have to go through power rule. But before we get through power rule, we got to take care of a couple of things. The square root is out of place. The x cubed is out of place. So they have to eventually move up to the numerator, but the 2 and 3 stays. Okay, so only the x moves up 1/2 and 1/3. That we can just push that out in front. So I set up using notations to indicate what I'm about to apply. I'm about to apply a power rule, and I'm also cleaning up. Okay, so as you clean up your expression, keep your integral in your dx notation. Right? Hold on to that as long as you can until after you apply power rule. Once you apply power rule, then those notations go away. Okay, so 5x to the 4th. I'm not going to change that. Just going to keep that. That's ready to go. Pi is ready to go. 1/2 root x. I made that x to the 1/2, and I pushed that x up to the numerator, so x to the -1/2. 1/3, that's going to stay in front. X to the 3 in the denominator becomes x to the -3. So now I'm ready. Every term is ready to go. Now I can apply power rule. Add 1 to the exponent divided by that new exponent. Okay, so as soon as you apply power rule, these notations, these bookend notations will go away. Okay, so 5x to the 4th becomes 5x to the 5 over 5. Pi becomes pi x. Remember, pi is a constant. It's like a 3 or 4. It's going to rise up to a degree 1. So pi becomes pi x. 1/2 pushes out, stays in front. X to the -1/2 becomes x to the 1/2. Whatever new exponent you have above, copy that number below. X to the -3 becomes x to the -2 over -2 plus c. I like having all those coefficients out in front. It makes it easier for me to multiply with any remaining coefficients. I can multiply the 3 and -2. That's nice and clean. The 1/2, I'm gonna push that up to the top as 2/1. Right, 1/2 in the denominator, setting as 2/1 in the numerator. And then reduce accordingly. So the 5's cancel out, x to the 5th. 1/2 times 2 is just 1, so that these two cancel out, which is left with x to the 1/2. 3 times -2 is -6. I could have pushed out that -6 out. I mean, I did, but then I also made that x to -2 come down to the bottom, so that's why I have the x6 and x squared together, since they're both sharing the same denominator space. Okay, number 7, antiderivative of trig functions. Let's do this. Let's find some empty space that you have on your paper that you can find. Let's see if we can recall our 6 trig derivative rules, right? We know how to line them up. Sine, tangent, secant, and then the second column are your C functions, C trig functions in alphabetical order, COS, COT, CSC. You can find each of those derivatives, because if you can find these derivatives, you're just reading them backwards to get to all your integral rules. Okay, so if we have these rules in front of us, this is all we need to answer the questions that we're going to do here tonight. Okay, so we're going to take the antiderivative of negative cosine x plus 5 sine x minus 5 cosecant. So I'm going to set up my notations here to show what I'm about to apply. All right, so what's cosine going to turn into? Good, so it's cosine, right? We'll start on the right side of our derivative rule, so we'll move to our left. The antiderivative of cosine is sine. The cosine becomes sine, the -2 just hangs out in front and stays. Right. What's sine going to turn into? Sine becomes a negative cosine. The negative has to go somewhere, so it's going to tag along with that cosine. So this will become minus 5 cosine x. And these two, we got to get used to, right? That these are not what we expect from derivatives, right? We expect cosine to change to a negative sign. We expect sine to turn into a positive cosine in terms of derivatives, right? But this is antiderivative, so going backwards, the sign is going to be different than what we would expect. And finally, cosecant, cotangent, what does that turn into? Okay, becomes negative cosecant, right? Because we're starting on the right side, moving to the left. The two negatives will cancel out, so that's why it gives me a positive 5 cosecant x. Number 8, find the most general definition or general expression. So we're starting with f double prime and moving up our way up the chain to f prime and then eventually up to f of x. Okay, so for number 8, we just go ahead and we start off indicating what we want to do. We want to move our way from f double prime to f prime. But to get to f prime, what I'm going to do is I'm going to take the antiderivative of this expression. So I'm just going to indicate on the right side what I'm about to apply. I want to apply that antiderivative rule and transform that expression up to the function level, up to f prime level, sorry. This right now, this expression is sitting at the second derivative level, but once I apply that antiderivative, this expression will transform into the f prime function. So I'm going to apply power rule. Once I apply power rule, then I'm going to be halfway through my problem. I'm going to be up at the f prime level, still needing to go to my f of x. Okay, so every term gets applied power rule. 4x cubed becomes 4 to the 4th over 4. 5x squared becomes 5x cubed over 3. 3x becomes 3x squared over 2. What does the 6 become? 6x, right? Every degree rises. A constant is going to rise up to a degree 1. And then we don't want to forget a plus c. Plus c. As soon as you apply your antiderivative power rule, your bookend notations goes away, right? In the place of it, you have a plus c. Do some more cleanup. That will take us to our halfway point. Now I'm going to move up to f of x to go to f of x. I'll say f of x equals the antiderivative of this expression. So now I'm just one power rule away to get from this f prime function into the f of x function. Okay, every degree gets increased by 1. X to the 5th over 5, x to the 4th over 4, x cubed over 3, x squared over 2. What happens to the c? Cx, but this process will produce its own what? Its own plus c. So it'll be plus cx plus k, or you can say plus cx plus c sub 2. All right, any questions with 8? Okay, number 9. It's just fine. It says find the specific expression. This expression is basically at the f prime level, and we just have to find the antiderivative once. And then once we take the antiderivative, a plus c will show up, but we have an order pair to help us find that c value to get it from general to specific. So I'm just going to follow the notation here. F of x is the antiderivative of g of x. Well, I know what g of x is. G of x is just this expression. So I'm just going to rewrite my integral with my g of x replaced. So if I can resolve this, then I'm sitting at the f of x level, and I can use this order pair to help me solve for c, and then I should be able to get my full specific expression for f of x. So I'm going to apply power rule here. Okay, so now how can I use this order pair to help me find c? Replace x with what? -1, and replace f of x with 2, right? Or my y value. F of x is my y, right? So 2 goes in this space, -1 goes in for the x's, and I can solve for c. Once I can solve for c, I can just rewrite my function with the c replaced with a number. Any questions here? Okay, let's go to worksheet 2, page 9. Right, I got you guys have keys attached, so you guys can look. I'm going to pick and choose problems on page 9 here to do. I'll skip number 1. That's just a matter of plugging values in and adding up. Let's look at number 2 here, where we have to work backwards to try to create that sigma notation. A couple things to keep in mind when you're looking at patterns here. Look for possibilities of maybe involving multiplication, or maybe it is an I raised to a power, or it is something like 4 raised to the I. Something like that, right? Just explore those possibilities, right? Maybe it is an I raised to a power, maybe it's a constant raised to an I, or it's a multiplication factor of I. So I like to start off with my sigma notation. I equals, let's say 1. We'll just test starting with 1, see if that will help us get there. And then I like to put in place the parts that are not changing. So it kind of gives me a framework, kind of gives me a starting point. So what's not changing throughout all of these terms? The 5, the minus, and the square root. So I can just go ahead and put all that in place, right? I know those aren't changing, and that kind of gives me a skeleton to kind of work off of. And I know that everything that is changing is going to have to be some sort of has to involve I, right? Because I is the variable that is that's forcing these values to change. So I know I'm going to see, okay, ideally, I equals 1 will produce this expression. I equals 2 will produce this expression. I equals 3, and then I equals 4. Right. So the numerator, I think that's a little bit easier here. What can I put in here that will produce a 2, a 4, a 6, and 8 involving I? 2, I, right? Let's double check it. So 2 times 1 is 2. That's good. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. Right? What about the denominator, though? What's that relationship there? Right. So 1 squared, 2 squared, 3 squared, 4 squared. And what's my upper bound? 4, because 4 is the highest I value that I can plug in to get to this last term. Okay, number 3, use 3 left-handed rectangles to approximate the area of the region bounded by f of x. So first, start off by building your width. Width is b minus a over n. What's my n value? 3, because I have 3 left-handed rectangles. Okay, width is 4/3. Where do I start to build my subinterval here? Start at 3 and keep adding 4/3. So 3 plus 4/3, the same thing as 9/3 plus 4/3, which is 13/3. Plus 4/3 is 17/3. Plus 4/3 is 21/3, and 21/3 is same thing as 7. Now in this case, we can just stop and insert and find the left-handed rectangles. But if it was asking for middle rectangles, then you would have to find the average of these two numbers. So add these two, divide it by 2 to get the midpoints. But in this case, we can just rely on the left endpoints. So this is my first subinterval, my second subinterval, my third subinterval. Every rectangle, it has a width of 4/3. So I can factor that 4/3 out and then just add up all the heights. First subinterval, the left endpoint is the 3, so f of 3 will give me the height of my first rectangle. Second subinterval, I want to choose a left endpoint, so f of 13/3. And third rectangle, height is f of 17. F of 3, insert into the function. F of 13/3, insert into the function. 17/3, insert into the function. Get all these decimal values, add and multiply together. Right, make your calculator do the work for you there. Okay. All right, number 4, let's get some more practice with Riemann sums, table of values. Again, when you're doing table of values, do not use this formula. B minus A over N is not used if they give you a table of values, right? You're going to be just separating the intervals and finding the width on your own. You're not going to be building the width if they already give you this information. Yeah, I'll pass it. I'll pass those out. What I want to point out with trapezoids is again, we can't use the trapezoid rule. We have to do two separate trapezoids area formula because the width is different and there's only two heights associated with each trapezoid. So we don't want to do 8 plus 3 plus 1, just 8 plus 1 for the first trapezoid. Second trapezoid is just 1 plus 5.
If it's dark enough, like, if you just have it on table, do you just draw off the table for each?
I will draw out, I will give you a space where, you don't have to, and I'll also just make it easy. I'll copy this table for each problem, so you can kind of just do the work. Okay. Yeah, so you're not gonna, I just did that to show the. I'll give you I'll copy all the table for each problem, for each part. Okay. Okay, I want to give this out to you. This is the morning review that I just did this morning. Yeah, just with the remaining time here, I just want to go over one of the problems that I had that I went over this morning. And just want to quickly run through number 2. Number 2 is a power rule problem, but it does require having to split up into individual fractions. Okay, so first things first is to get all those radicals resolved, but we're also got to figure out how to split up the fractions and also bring the denominator up. Okay, so the cube root of x becomes x to the 1/3, the square root of x becomes x to the 1/2. can split this up. This is too messy of a problem to handle with one power rule, but we can split it into 3 individual problems. So every fraction will have, every term will have a denominator of 4x to the 1/2. Okay. Now, what comes up from each of those terms? Just x to the 1/2. Okay, what stays? 4. Good. So the 4 is just a coefficient. We can push those out in front. It's the x that we have to clean up. So all when the x's come up, they all come up as what power or what degree? X to the what? Good. Negative 1/2. So the x negative 1/2 comes up. They all come up, but I can push all those coefficients out in front. There's a 5/4 in front. There's a 2/4, which is 1/2. There's a 1/4. And I just have to figure out how to get those x's together. To get those x's together, I have to do up the exponents. I gotta do what? Add, right? Now to add exponents that involve fraction, I need to find what common denominator. So 1 minus 1/2 is 1/2. 1/3 minus 1/2 is 2/6 minus 3/6. 5 minus 1/2 is 10/2 minus 1/2. Okay. And then once you get all those fractions resolved, now you're ready to do power rule, right? Because there's no more multiplication that needs to be applied with all the x's. All the denominator has come up, parentheses resolved, okay? And radicals resolved as well. Okay. Now we can do power rule. So add 1 to the exponent, divide it by the exponent. And if, with all those messy denominator fractions, we can flip them up as reciprocals and then multiply, clean up. Okay. As soon as you apply power rule, your integral and your dx notation goes away. You're just left with a plus c at the end. Okay. All right. Tomorrow I have a help session, morning help session to go over review worksheet 3. Okay. 7:30 in the morning. Come and get your phones.
They were in the like a but like you just and so these are like this waiting and just trying
All right, good.
But that's why we were.